Welcome to Spring LIB.
This is chapter 37, problem number 66. We're given a set of measurements of frequency coming from 4 different sources. And in part A, we're asked to calculate the source, to determine the source that has the highest speed relative to the detector. So highest speed relative to the detector, which means we're going to have to find the speeds for all the sources that we have. And then we would be answering the next question. What is its speed? And is that source moving towards, is it moving towards or away from the detector? Now, if you look at the data set that is given to us, you're going to notice that F naught is always greater than F for all sources, right? Which tells you from the get-go, if this is the case, that all sources are actually moving away from our detector. Okay, so we kind of answered the last part. We kind of answered this question. Now, what we need to do is, since now we know that all the sources are moving away from the detector, we're going to write down the relativistic Doppler equation. F equals F naught square root of C minus V, C plus V, right? And then calculate what V is, this guy, for each source. In order to do that, let's rearrange this equation and write it in terms of V. Okay, so let's divide both sides by F naught. These are going to cancel. F over F naught is going to be equal. Let me just erase this. Let me show you what I want to do on the equation that I put there. So then I need to get rid of the square root. So I'm going to take the square of both sides. Then on the left-hand side, let's switch sides. C minus V over C plus V then is going to be equal to F over F naught squared. Now let's multiply both sides by C plus V. Okay, C plus V, C plus V. So these are going to cancel out. Then C minus V is going to be equal to C plus V times F over F naught squared. Now I'm going to distribute these terms. C minus V equals C times F over F naught squared plus V times F over F naught squared. Now we have 2 terms that has V in it and 2 terms that has C. So I'm going to take this term to the left-hand side. C minus C F over F naught squared is going to be equal to V F over F naught squared plus V then, right? So let's group this right-hand side. When we do this, it's going to be V F over F naught squared plus 1 equals to C1 minus F over F naught squared. So let me write down this equation on the next page nicely. The component of this is 1 plus F over F naught squared equals to C1 minus F over F naught squared, right? So now if I divide both sides by 1 plus F over F naught squared, and this side too, these are going to cancel, so I have my expression for V. So it's going to be C times 1 minus F over F naught squared divided by 1 plus F over F naught squared. This is the equation that we're going to use for all the sources that we have. So then let's start doing it for the source A. So for source A, let's read the table. For source A, F equals 7.1 terahertz and F naught equals 9.2 terahertz. Now let's look at our equation. C, let's leave the speed in terms of c, so I'm not going to plug it in for it. 1 minus 7.1 divided by 9.2 squared over 1 plus 7.1 over 9.2 squared. If you do this correctly, then VA, let's call it VA, the speed of the source A, is going to be equal to 0.25 c. Now I'm going to do the similar, I'm going to apply this formula to other sources as well. Then let's go to the next page. For source B, F equals 5.4 terahertz, and F naught is 8.6 terahertz. Then in our equation, V sub B equals C. Again, I'm not going to rewrite the equation. Let me plug in the numbers. So it's going to be 5.4 over 8.6 squared divided by 1 plus 5.4 over 8.6 squared. So from here, for the speed of the source B is found to be 0.43 times c. Okay, this is VB. All right. Now for source C, F equals 6.1 terahertz, and F naught is 7.9 terahertz. So then the speed for it is going to be 1 minus 6.1 divided by 7.9 squared divided by 1 plus 6.1 divided by 7.9 squared. Now the speed for the source C is found to be 0.25 c, just like the source A. Now for source D, F equals 8.1 terahertz, and F naught equals 8.9 terahertz. Now VD then is going to be C times 1 minus 8.1 divided by 8.9 squared divided by 1 plus 8.1 divided by 8.9 squared. Then from here, we find it to be 0.09 c. Now, what we said, VA, let's do a recap. It was 0.25 c. VB was found to be 0.43 c. VC was found to be 0.25 c, and VD is 0.09 c. Now, we have found the answers to part A and B, by the way. So looking at here, remember what was asked in part A, highest speed relative to the detector. Then the highest speed is obviously coming from detector B. And what is its speed? Well, its speed, let me write the answer here, detector B. Its speed is 0.43 c. And remember from the beginning, we had already answered, is it moving towards or away from the detector? It is moving away from the detector. Now in part B, we're asked a similar question. Which source is moving at the lowest speed relative to the detector? Which one is it? Obviously, it is this one, right? It's the smallest of all. So detector D with the speed of 0.09 c is the it has the lowest speed. What is its speed? Well, we answered. Is that source moving toward or away from the detector? Again, away from the detector. Now, part C is asking for something else, actually. So in part C, we are asked to calculate the frequency for source B. What frequency would your detector measure if the source were moving at the same speed relative to the detector, meaning VB, remember what it was from here, VB was 0.43 c. 0.43 c. Imagine that this is the speed at which it's moving relative to detector, but rather towards the detector rather than away from it. So now we we know the F naught, right? It was given to us 8.6 terahertz, and now we are to calculate the frequency, assuming that it is not moving away from the detector, but it's moving towards the detector. So what happens when we assume that it's moving towards the detector is that the shape of our equation is going to be different this time, right? This time we are adding C to V, and then in the denominator we're subtracting. Now 8.6 terahertz square root of C plus 0.43C over C minus 0.43C. When we do the algebra, what we get is 13.62 terahertz. That's what our detector would measure if source B was moving towards the detector.